Oh my God. All right, this thing is working finally. All right, so this is the one that I'm gonna get to use. All right, so you got this loop right here. All right, this is a loop of wire. What I'm gonna do is I'm gonna increase the strength of the magnetic field within. All right, so here's one magnetic field line, here's the second one, here's the third one, fourth one. And then what's gonna happen is as soon as I try to increase the strength of the magnetic field within this, the current is gonna move in a direction that's gonna oppose that change. All right, so here's the magnetic field. All right, so this is the magnetic field coming out of the page. All right, so I'm increasing the strength of the magnetic field within that region. So what's going to happen is the current is going to move in a direction that's going to oppose that change. So which means that the induced magnetic field, remember guys, these are vectors. All right, so in this case, the vector is coming out of the page. So there's going to be an induced magnetic field. It's going to oppose that change. So the induced magnetic field is going to go into the page. If I increase this by 1, the induced magnetic field is also going to increase by 1 in the opposite direction. So it's going to cancel out that change. So there's going to be an induced magnetic field pointing into the page. So this one is going to be induced. So which direction does the current need to move in order to generate an induced magnetic field? And as you all know, the current needs to move in this direction so that there's an induced magnetic field going into the page in that direction. All right. So the induced current is going to be moving in this direction in order to cancel out the change in the strength of the magnetic field. All right. Okay, so let's change the scenario a little bit. We're going to delete this one. All right, so just get rid of that. All right, so this is still our current loop. There. Okay, so what would happen if I were to actually reduce the strength of this magnetic field right there? Okay, so which means that I'm going to diminish the strength of the magnetic field. So I'm just going to make this. All right, so the strength of the magnetic field is diminishing in this case. All right, I'm going to change the notation a little bit. Get rid of this. All right, so what I'm doing is the magnetic field is coming out of the page. I'm just diminishing its strength. All right, so I'm putting a minus sign. So the strength of the magnetic field is going down in this case. All right, so what's going to happen is in order to cancel out the change in the strength of the magnetic field, now the current needs to move in a direction which is going to oppose that change, which means that this time the magnetic field is going to be coming out of the page. So the induced magnetic field is going to be coming out of the page. And for that to happen, the current, which is going to be responsible for that, has to move in this direction. All right, so the induced current is going to move in a direction that's going to oppose any change in flux, any change in flux, in essence, or it's going to oppose any change in the strength of the magnetic field. Okay, so Lenz's law, you got the statement here. So it says induced current is going to move in a direction that's going to oppose any variation within the strength of the magnetic field inside the loop that we're looking at. All right. Here, I'm increasing the strength of the magnetic field intercepted by this area. Now the current needs to move in a direction that's going to oppose that change in magnetic field. So the current needs to move in this direction in order to oppose that change. So which means that it's going to create a magnetic field, induced magnetic field, opposing the increase of the magnetic field within that region. Here, I'm reducing the strength of the magnetic field intercepted by this area. All right, in order to actually oppose that change, the current has to move in this direction in order to reinforce an induced magnetic field in the direction of the original magnetic field. All right, so that's the concept. And you have to kind of play with the concept until you kind of get used to it. All right, so that's exactly what we will do now. All right, so let's get back to this one again. You're increasing the strength of the magnetic field, so the current is going to move in a direction that's going to oppose that change the magnetic flux. All right, so as you start to increase the number of lines, magnetic field lines in this direction, the induced current is going to generate its own magnetic field lines in the opposite direction because the magnetic field lines are vector fields, obviously. So they will, in opposite directions, they will cancel. All right, so visually, this is what you got. You got ring, metallic ring. It's just following this direction under the influence of gravity, and there's a constant magnetic field agent. Normally, there's no current inside the ring. and there's no current inside the ring. But as soon as it starts to enter into a constant magnetic field region, what's happening is the strength of the magnetic field is varying here, so the current is going to move in a direction to oppose that change. As it's leaving the region, once again, the strength of the magnetic field is by this area is going to change. So the current is going to move to oppose that variation. All right, notice that the current moves in one direction first as it's entering into this region, and then the direction of current actually changes as it's leaving this region. Within this region, there's no current inside the ring because the strength of the magnetic field is not changing. All right, so this comes about because of the Lenz's law.
Not only can electromagnetic induction stop a piece of metal, it can get one going again. Because a piece of metal doesn't like to be in a region of strong changing magnetic field, which I have right here. If I take this ring of aluminum and put it down in the field and turn it on, you should actually be able to see the aluminum jump when I turn the field on. You ready for this? Here it goes. Watch. There.
All right, so let's
not only can I let the field on. You ready for this? When I turn the
aluminum is not magnetizable. All right, so you cannot turn an aluminum into a magnet.
Field on. You ready for this? Here goes. Watch.
So why is the aluminum jumps as soon as he turns on the current?
There. Watch. Turn the aluminum jump when I turn the field.
All right, so what do you have here? You got an electromagnet, and then as soon as you turn on the current, what's going to happen is the strength of the magnetic field intercepted by the slope is going to vary, right? So there's going to be a change in flux here. So the change in flux is going to induce a current within the ring, which is going to oppose that change in flux, which means that the ring is going to generate a current, which is going to move in a direction that's going to try to cancel out that change in flux. So the opposing magnetic fields will end up generating that.
You ready for this? Here goes. Watch.
Propulsion that you're looking at. All right, so there's going to be a current which is going to be created inside
when I turn the field,
the aluminum ring. And that current in turn is going to generate its own magnetic field, which is going to try to oppose the change in flux within the loop itself. What do you suppose would happen if I were to just put a gap here inside the aluminum? Do you think it's going to be able to generate a current that's going to oppose the change in flux? What do you guys think?
Hold on. You ready for this? Here goes. Watch. There.
If I were to place a gap inside the ring, do you think it's still going to work?
No.
Okay, so Ian, you say no. Why not?
Because the current wouldn't flow.
Okay, because you wouldn't have a loop, you wouldn't have a circuit, right? If there's a break in the middle. So the current is not going to flow. Give yourself 5 points for that one. Give yourself 10 points for that one. All right, so this is the same experiment that we were looking at. So this is an aluminum ring, it's a magnet. The magnetic fields are opposing each other, so that's the reason why you end up getting levitation out of it. But as soon as you place a gap in the middle, you're not going to be able to form a current loop. All right, so if there's no current loop, there's no current, so it's not going to be able to generate an opposing magnetic field. Okay, so nothing happens. All right, so that was a nice demonstration. All right, so following magnet in a copper tube. Copper, once again, is not magnetizable.
This is Lenz's law kit. It demonstrates very nicely how magnets behave when they fall down metal tubes. We have a slug of metal here, and we're going to drop it down the tube, and there's a nice window in the tube, so you can see it all the way down. Oof, down she goes. Turns out up, and still it's going to go down at good speed. It's called gravity. Well, now, if we were to make a magic pass, drop it down again, something else might happen. Look at that. Extraordinarily slowly. And the other way up. Oh my, oh my, oh my. Well, of course, there's a sleight of hand. This is highly magnetized, and this little buddy I showed at the beginning is not magnetized at all. The highly magnetized one...
Okay, so when you use a magnet and drop it through a tube, a copper tube, why is it that it's slowing down?
It's creating a little eddy current in the tube, which itself creates a little magnet.
So it's just going down. What's happening? Every single level acts like a current loop, right? What's happening is the change of flux is going to generate these eddy currents. And eddy currents will generate an induced magnetic field opposing that change.
Magnetic field that opposes the descending slug of metal, and it's trying to stop it going down. A nice demonstration of it, too. Lenz's law kit.
So find this one. This is motional electromotive force. Okay, so this is the voltage which is going to be created by the motion of a conducting rod. All right, so you got your conducting rod. All right, so this is in essence a piece of metal, and you're dragging it inside a magnetic field. So the magnetic field in this case is pointing into the page. All right, so you are moving this in this direction at a given speed. All right, I don't see V there. All right, so let's just indicate that this thing is actually moving in this direction. it's experiencing a force in that direction. That's weird. All right, so it's being moved in that direction. Okay, so the first thing to do is just focus on a positive charge. So you got this positive charge within this region. Oh, evidently B is here. All right, so good for us. All right, so what's going to happen to this positive charge? The magnetic field is pointing into the page. And the positive charge is moving in this direction. All right, so the magnetic field is pointing into the page. And this is moving in this direction. Okay, so using the right-hand rule, what happens? You line up your thumb in the direction of the velocity vector. The fingers will point in the direction of the magnetic field. So your palm is going to point in the, it's going to face in the upward direction. So which means that the magnetic force is going to be in the upward direction. So these charges, positive charges, inside the metal piece will experience a force in the upward direction. So positive charges will move up in this direction, and negative charges will experience a force in the downward direction. So the negative charges will move down in the opposite direction. Notice that the positive charges will accumulate on top. The top is going to be positive charge. The negative charges will accumulate at the bottom. The bottom is going to be negative charge. So which means that there's going to be an electric field in this direction. So there's an electric field in this direction. And notice that there's a separation distance, which is L, that you're looking at. So you got the electric field here, separation distance there. Strength of the electric field times the separation distance is going to give you the voltage difference between those 2 points. So which means that this metal rod becomes a battery. Okay, so it turns into a battery because of its motion through the vehicle motor force. It's going to act like a battery. It's going to behave like a battery. So it turns into a battery. Charges will become separated. This becomes like a positive terminal. This becomes like a negative terminal. There's going to be an electric field strength in this direction, and there's a separation distance, which is L. Strength of the electric field times the separation distance is going to give you the voltage difference between those 2 points. All right, so conceptually, that's what this story is. Okay, so what do we know? It says here that the charges will separate until the magnetic force and the electrostatic force act with each other. All right, so this becomes a starting point. The electrostatic force on these charges is going to be the strength of the electric field times the net charge, and you got an expression for the magnetic force. All right, so I'm just going to skip the details and just jump into the conclusion of it. All right, so the conclusion is this: the motion of the conductor, and this is the velocity of the conductor inside a magnetic field, and this is the length of the conductor, is going to make this conductor behave like a battery. All right, so because of the motion of these charges, because of the motion of the conductor, the charges will become separated. One end is going to become like a positive terminal, the other end is going to become like a negative terminal. The separation distance times the strength of the electric field is going to give you the voltage difference between those two, which is going to be generated by the motion of the conductor inside the magnetic field. And this is the length of the conductor. That's it. All right, so the derivation itself is not that important, but the end result is. So what that means is, while you're driving your car is a conductor. And obviously you're going through the Earth's magnetic field. The car also becomes like a little battery in a sense. So the charges also become separated on the surface of the car.